Shall we get started?
Yep, we're good to go. Yep.
Okay, thank you. So what we're going to cover is the practicum on the Gans that I think Alfredo covered. So let me just share my screen and go into that. Feel, I am by no means an expert in this. I'm just leading this, so feel free to jump in and clarify and keep me honest. But my aim is just to go through some of the videos and kind of like some parts of the video and the notes, and to clarify, just foster discussion that we have. So with that, hopefully you guys can see my screen.
Yes.
Okay, thank you. All right, cool. So I think we're going to start off with the diagram I think that Alfredo had, and then we're going to talk about what the differences are with the different types of autoencoders. So if you look at the diagram, what we have here is the diagram of a typical high-level GAN. Here, the pink X refers to real input. If we use the analogy we used last week, it's the real currency, the images of the real currency, or the real images, or whatever. It's the real data. Whereas the X hat, on the other hand, is the simulated or the fake data that's created by the generator. Now, the generator generates that by sampling the Z or the Z space. So it samples it. It uses basically noise and a sampler, feeds it into a generator, and then it produces fake data. And then you have a cost function that basically I'm trying to avoid the word discriminator, because I think that they on the actual video they had an issue with the word discriminator, but essentially this is a discriminator by any name. And the discriminator, basically its role is to identify fake or real X, i.e. X or X hat. It does this, and actually, let me stop there. I think the issue that they had with the discriminator is based on terminology, because I think the word discriminator typically is a classifier and implies binary or distinct classes. So I think that they wanted to actually use the name cost function because it was more of a continuous space. I think that was the issue that they had with discriminator, but I'd welcome feedback. Does that sound about right? Okay. I'm not sure if you guys picked up on what their concern was with the word discriminator, but I think that was a concern, even though the code is full of the word discriminator. Any comment on that? Anybody you want to jump in? No? Okay.
Yeah, you're right. I mean, that's the comment. Yeah.
So what then we have is, and I'm kind of like going to the notes here, essentially is a type of a neural network for unsupervised machine learning. So what we have is two portions of it, I think we discussed last week, which is a generator and, what for ease of use, I'm going to call a discriminator. Even though I think that that's a loaded term that they have some issues with. The role of the generator is to generate data which is as close to the real X. So X hat should be as close to X, so that the discriminator is fooled, whereas the discriminator is supposed to pick up the differences. So essentially this is adversarial. The generator tries to fool the discriminator tries to pick up tries to identify real versus generated data. So I'll kind of skip into the diagram here. So my view of the diagram is this pink line is the essentially the manifold of real data. So X lives on top of that manifold somewhere. Okay, that's the area where it lives, and that's the area of low cost. And then X hat is anything outside of that manifold. And that's what's generated. Let me just kind of segue straight into the differences. So what we previously had, and let me kind of like pull this up, make it a little bit bigger, hopefully make it easier for you guys to see. So what we had with something like a variational autoencoder is, this is the X space, and this is the latent space Z. So, I'm not sure if I'm talking to people from the UK or people in America. So just if you hear Z or Z, use them interchangeably. So this is the Z space. So with the variational autoencoder, what we did is we started on the manifold, and that is like a real X. We encoded it and landed on the Z space. And then we used a decoder to map it back into the X space, and we landed somewhere in the X space, and that's the X hat. So the loss function is the reconstruction loss, which is the distance between X and the reconstructed X, which is X hat. So the process was we started in the X space, we mapped it to Z space, and then we mapped it back. And we tried to minimize the distance between them, the reconstruction loss, so that X hat and X are the same. So that at a high level is what we covered in terms of variational autoencoder. Before I move into general adversarial network, any questions? I'll just about variational autoencoders. Does it make sense? I was kind of rushing through it. Okay. So what we're doing with a generative adversarial network, or just a simple GAN, is we have the manifold in the X space that defines essentially the valid data. On that manifold, the data is all low cost. X hat is everything outside of that manifold. So what we really have is, we don't start from the X space on the left side, map it to the right Z space, and map it to the left. We actually start on the right-hand side. We start in the Z space. So we're sampling the noise, then we generate data. Essentially, you can think of it as like through a decoder, and we land somewhere in the X space. Now, initially, that's going to be a random location, because you have no idea where you're going to land. But what you're trying to do here is, by using adversarial techniques, you're trying to have the generator learn how to minimize the distance and actually get to the manifold, to get to the low cost space. And we'll kind of go through that, but I just wanted to kind of rewind and say the main difference between the VAE and the GAN was because you start from the left, go right, and back to the left, whereas here you start from the right, you map it to the X space. So start from the right, map it to the X space, and then the cost network is basically providing feedback to identify how close to the low cost space you land, to the manifold you land. Does that make sense to everybody? Any questions on that? Any suggestions? How could I have done it better?
So the decoder of a variational autoencoder and the generator are kind of equivalent, right? They just take a random Z variable and generate something realistic from that.
Yeah, so a variational autoencoder, it does actually, for a variational autoencoder, that's the key term, it actually samples, essentially from a normal distribution and generates noise and uses that as an input to then generate the X space. That's what a decoder does. To me, the decoder and the generator are pretty much the same concepts, but with a VAE, essentially the decoder is essentially going back. Essentially, its job is to undo what the encoder does. Whereas in a GAN, there is no encoder. You're just basically generating some sort of a mapping back to the X space. And the concept is the same, I believe. But there is no encoder in the space.
So can you take a decoder separately and just use it like a GAN to generate realistic images?
That I think is exactly what's in the code. We're just taking. I'm sorry, I just was to say. I mean, a decoder basically is going to upsample from the Z space and try to get back to the X space. So in that respect, they're the same. But it needs to be trained in a different way. I'm sorry, I interrupted. I forget who was talking, Stephen or something.
I had a point there. I think the generator has an easier or a harder job than the decoder. Mainly because when you do the decoder, it is sampling from a real, a distribution around the real input, right? So there is more of a point, the distribution around a certain point. Whereas with the generator, it's generating or sampling something from pure noise initially, right? And it's the feedback that you get from the discriminator that kind of trains it back. So that was something I thought.
I'm just not clear on whether it's samples from the real input. So the input space is X. You map it to Z, and then you sample in the Z space, and then you map it back to the X space. So you're mapping, you're sampling in the Z space.
Yes, you're sampling in the Z space, but you're still sampling based on, so X gets transferred to or transformed to Z, and X gets transformed to AZ, and and then you sample from the distribution around that Z. Yes, I mean I think that's maybe right. Yeah.
Okay.
Yeah, I agree with what Sujit is saying, right? Because if you look at the left-hand side diagram, the Z comes from an encoder of X plus some noise. So it's not unconditional. If it were unconditional of X, then the the generator would more resemble the decoder. But if you look at the diagram, on the left-hand side, the Z comes from an encoding of X plus some noise. So X is a factor in the Z on the left.
Got it. Okay, that makes sense. Okay. So let me kind of go back to here. So I thought it'd be worthwhile kind of like going into the differences. Let me make this a little bit smaller. So I thought it'd be easier to kind of like understand this diagram if we compare it to a variational autoencoder. So hopefully that makes sense. They're described as energy-based models. And I think last week, before last week, I was very skeptical as exactly what the paradigm of an energy-based model is. I'm a little bit more comfortable, but I'm still not convinced that the construct has any practical value or help with understanding things. Anyway, I'm just throwing that out there. And just, the concept of an energy-based model, it's like, that's great. We just give it another label. Does it really help us with our understanding? And I'm a little bit skeptical still, but
so is that just a way of implementing GANs, or is it just GANs in general? So like, is EBM a way that you can write GANs?
No, they're just saying that GAN is a type of EBM. That's what they're saying.
Okay.
So in the Z space, there is no right or wrong. There is actually areas of high-low cost or high-low energy, and you're essentially inferring the low energy portions of Z space. So that's my understanding. I don't know if anyone wants to jump in.
GANs, at least at the initial, while it's training, right, when it's starting, GANs generate guesses, right, or forgeries or what have you, from pure noise, right? It's only later that they are able to learn the structure of the latent space sufficiently from feedback from the discriminator that they are able to transform pure noise into something resembling the distribution. So in effect, they are learning the distribution of the input from nothing, right? Or from feedback from the discriminator, right? So that's my, yeah.
Okay. No, I was just questioning the concept of an energy-based model, but I think we spoke about it last week, so I won't dwell on it too much.
Yeah. Well, I mean, in this case, the energy is kind of diffuse, right? So the input to the GAN, the energy input to the GAN is kind of like, there is no structure there, right? So that's.
So another question. So in energy-based model, don't you have to like do gradient descent at inference and all of that stuff? Only then it becomes an actual energy-based model, right? Or do you just call everything as energy-based model?
I think the latter.
Okay, but by the definition, yeah.
Sorry, go ahead.
No, I thought that's how they are defined as, like during training you have you basically define what your energy function is, and then during inference you get the y by minimizing by gradient descent, by doing gradient descent on the energy function.
Is there any difference then between energy and loss? Or does Jan LeCun just call everything an energy-based model and defines energy, high energy is like high loss and low energy is low loss?
I mean, it is confusing, but I think there is a difference. Basically, you don't do gradient descent during inference time, right? You just feed the x to a model, and just whatever comes out is your output. But in energy-based models, during training you create the energy function, and during inference you perform gradient descent again at inference time to get your y. But I understand the other point as well. It's just a reformulation of, it's just a different way of looking at it, but I feel that there is a difference. Yeah, but someone else can give out their ideas as well.
Yeah, at least my understanding is I don't think what you do is different depending on whether it's an energy model or not. What you do, at least so far that I've seen, is no different in the two approaches, at least up to Gans. Gans is still a little bit confusing as explained from an energy perspective. I haven't fully grasped all the nuances of what increases and what decreases, but as far as a variational autoencoder, or even the variations of the variation autoencoder that Arto took us through, none of those seem different than what is explained elsewhere without the use of energy concepts. So that's where I tend to agree with what Joseph is saying. Is I'm yet to see a practical, here's what the concept of energy allows you to do, which is different and enhanced or improved in some way, or enhanced, which I think Mayank pointed to last time, but I haven't gone through that yet. So from what you do perspective, I haven't seen anything different, subject to what we discussed today.
It's an interesting concept. Okay. Yeah. Sorry. I interrupted somebody, no?
No, that's
okay. So let me kind of move on. Okay. Okay, let's just quickly finish this section, which is basically, I think we covered most of this, but basically the Degenerate network is trained to improve the mappings from the Z space back to the X space, so that's close to the manifold, and it's generating X hat to trick the cost network. And one thing that I wasn't exactly clear on is the loss function. So let me kind of go back to this this diagram and kind of go back into it. Okay. So the discriminator essentially has a cost function, and the cost function is supposed to be low when when it's an X input, when it's real input. But when it's X hat, it's fake data generated by the generator, then the cost is supposed to be very high. So the purpose of the cost function is to just basically provide a huge number if it's fake data, or like zero if it's real data. So we train the generator based on the cost function. That's my understanding. But then the discriminator takes as its input the cost function and uses a loss function on top of that to train, so you can train the actual discriminator. So so if we kind of go back to the loss function here, the cost function is defined as the cost of the real input plus a huge arbitrary number minus the cost when it's fake data. So GZ is X hat, right? So the output of the generator is X hat. So when it's identified as X hat, the cost should be high. So the overall cost is going to be the cost of that minus the cost of, plus the cost of the huge penalty minus the cost of that. So I wasn't really clear how this formulation helps or why it's set up this way. I'm not sure if anybody wants to jump in, because the way what I'm thinking is, if it's the cost, if it's X, right, then the cost is going to be 0, and this is going to be high. But if it's fake data, then that, yeah, I was really sure about this. And I'm not sure if someone could just explain to me how the formulation of the cost function, why it's done this way. I'm sure if anybody knows Gans better than me, he probably wants to jump in and kind of like mention why the cost function is defined this way, or the loss function, I should say.
I can take a shot at it. So if you consider C as, I mean, you might have to look at this from an EBM point of view. So if C is your energy function for a real X, the energy function value will be low, right? For the data points, the value of the energy function is low. So Cx would be low for real X, and when your generator is producing unrealistic images, CGZ would be high. But if it is producing realistic images, just a minute, then your CGZ would be low as well, which means your total loss will be low.
Okay. So imagine.
Sorry, Gautam, but my understanding is I don't know the answer to Joseph's question of why it is set up this way, but at least the mechanics of this particular equation dictate that the cost of GZ should approach M. And as he explained in the lecture, to the X, and what we are doing, the plus sign on the top of the right square bracket means we're taking the positive part of that. And since we want the overall thing to be low, and like you correctly explained, cost of X is close to 0 when X is a real input. My understanding is you want the right side to be cost of GZ approaching M or close to M or slightly more than. When it becomes slightly more than M, then the entity or the scalar within the square brackets is negative, and since we are taking the positive part of that, that goes to 0. And C of X is anyway low, and that will be the lowest of the loss function. So in that sense, you want C of G of Z, the cost of the generator function, to approach M, therefore increase up to and slightly above M, approach M.
So,
But
sorry.
don't you want to minimize the loss?
Yeah, that was my understanding. We're not approaching 0, we're approaching M.
Right, but minimize the overall loss, right? And the overall loss is the combination of the left and the right parts. And the right part, I'm saying, is minimized when you take the positive part, and the positive part you take, which is when C of G of Z is just approaching M on the from one.
Okay, yeah. So the cost network wants the generator to wants high cost to be assigned to whatever comes out of the generator, and yeah, that makes sense, right? Because it wants to discriminate the output of the generator, whereas the generator wants its images to be I mean, the loss for generator is different. In that case, you would want CGZ to be 0. Does that make sense?
So if the input is X, right, then the loss is equal to what? What the CG equal? I mean, the
this.
I mean, you take both.
Just CX,
together,
right? That's just CX. But what would that be? It would be if I'm pumping in just X. Would CGZ be 0 because there's no X hat, right?
Yeah, you have to pump in both, I think.
Yeah.
Yeah, there's always a Z. There's never a case where there's no Z, because you're always, the generator just does generate an X hat from some Z.
But you're alternating between real and fake data. You're alternating between X and X hat, right?
No, I think you always have an X and a Z. So X is the real image and Z is a randomly sampled number. And to just to repeat what Srinivas said, the loss will be low when CX is, I mean, CX is 0, I mean, close to 0, and C of G of Z is close to M, right? Or slightly above M.
Okay, that makes sense. Okay.
Yep. Yeah. Here, M, or you can say is the here M can also be looked as in most of the cases we take M as 1 in the practical scenarios. So because we need to be since the values in the latent space are always taken between 0 to 1. So 1 is the margin with which you can have that space to put in a gap in which you have the the x and the x hat. So after that, this margin is the main thing here. So it's totally constructed as a min-max loss, and uh, the difference between min-max here, which is uh, based on some positive margin M, the other kind of losses, there will be the clear decision boundaries that we get every time you try to have this min-max game that is associated with the GAN objective. So when you're trying to sample from that space in which you have trained it in this way with respect to a generative or adversarial network versus a variational autoencoder in which you have some MSC or MAE loss, there the decision boundaries are fixed, and here it's kind of variable. So this will create a kind of a good uh, sampling space when you try to sample your uh, downstream tasks from this Z vector or the latent manifold that you have here. So in the end, this whole formulation helps in better values, but uh, nowadays this VAE objectives have come up to and exceeded expectations, and yeah, that is a bit how do I say it, more controllable here. But yeah, that's my rant. Thanks.
No, that helps a lot. Thank you, Mayank. Okay.
It could
One
be kind
thing.
of also.
Sorry, go ahead, Srini. Go ahead.
I was thinking that it could be something like the SVM idea, right? Where you're trying to train the cost function to be able to separate the two kinds of things. Therefore, you are insisting on some kind of margin that you're going to push. So any cost that the cost function generates based on x hat would have to be some distance away from the cost that a cost function generates from x. Right, so you are trying to make it learn to separate, kind of like a classifier, but with a more, MSE kind of thing around it, right?
Yeah, akin to a margin loss of
Yes,
some kind.
yeah.
Right? But what still is somewhat confusing to me is if the loss of the generator is simply the cost of the output, like C of G of Z. Now, as we have stated, to the extent that C of G of Z approaches M, so to speak, from the right side, meaning it's slightly over M, then the right side becomes, the second part of the equation becomes negative, and we take the positive part, which is 0. But then what is to prevent the cost of G of Z from just continuing to increase? Because if C of G of Z is much larger than M, then it would still be negative, which means that the right part would still be 0. So what constrains that guy? Because we don't want it to just keep growing. And if we want it to increase, then there has to be something which is constraining it to be just marginally above M. That's the part I don't get. How does that happen?
So that's the generator loss, right? The generator loss is simply CGZ, as it says there. So
Right.
you're trying to minimize CGZ as well.
But he's saying you try to increase, I thought, CGZ to approach
No.
M.
So the discriminator tries to discriminate them, whereas the generator will try to create realistic images, right? So they are opposing each other. The generator will try to create images which have low energy function value, which is low CGZ, whereas the discriminator's loss is lower when the CGZ is at least M. So they are like opposing each other.
Hmm.
Then this comment came up, which I don't think is part of the issues that was raised, that this does create instability because CGZ can bounce between 0 and M. I'd love to understand where that comes from. I'm not sure if anyone can clarify that.
Yep, this is the mode collapse problem, I think.
Oh, this is back to mode. Okay.
Yeah.
I thought it said bounce between 0 and M. I think it's saying that it could be any point along 0 to M. Okay. Cool. Thank you. That was a good discussion. That helped me understand this stuff a lot better. So getting back to the differences between GANs and VAEs, I kind of jumped forward and back. I think we've kind of covered this space, unless someone wants to kind of like go back. But I think we're reasonably clear on that. So then I wanted to kind of go straight into the major pitfalls in GANs. Is that okay? Okay, cool. So, I mean, the first one was the unstable convergence, which is, I think the primary point in this is that the discriminator essentially is classifying between real and fake data. As the generated data gets better and better, closer to real data, the classifier's performance deteriorates. So there's no clear way of deciding at what point we should just stop training because the generator has become so good, because the discriminator is incapable of figuring out at what point it's difficult to classify it. Essentially, you have two data distributions over time. They will overlap, and the discriminator is not able to put a decision boundary across anywhere, so it will just oscillate around that because it's unable to classify it. It will start providing random feedback. That's my understanding. I'll welcome other people's thoughts around that, and especially how that's actually mitigated in real life. I don't know if I could put you on the spot, Mayank, as I think you probably have the most knowledge in GANs, or I suspect you do. How is this actually handled in real life?
With respect to the unstable convergence?
Yeah, with unstable convergence, and how do you figure out that the discriminator has is just providing random feedback because it's unable to discriminate any longer?
Yeah, there are a couple of things that we specifically in the case of mode collapse and the generation when it kinds to come up to a particular point in which your network is unable to decide or it's like collapsing into a point at which your real data and the injected noise is unable to come up with some sort of it's unable to see the divergence between the x and the x hat as we have seen. So here the training convergence in Gans, it's referring to, I think, the ways in which you can set up your problem with respect to the backside and the practical aspects of training them. And here if we open this link, this training convergences in Gans, they have
this one.
yeah. Yeah, they have given the training procedures in the alternating periods with respect to firstly training the generator network for one or more epoch, then alternating it, and then back propagating the gradients, then stopping it, and then kind of like it's a hack here. It's not a hack, but it's the process here to get your network to learn as efficiently as possible. So in the high sense, if I look at it from 10,000 feet, then the interactability of the network with respect to the generator problems, we can solve this by the steps that they have mentioned here. Plus, there are a couple of research papers that take a look at the nitty-gritty of the training of a particular GAN networks, and they have how do I say it? They have uh, some steps which are required to uh, uh, efficiently train them. Let me try to find that, and I will paste it in the chat.
Yeah, thank you. If you could.
Yeah.
So yeah, let me kind of go back to this. So we've kind of covered unstable convergence. The second one I'm less clear about as well, which is the vanishing gradient. So the way it's explained, I appreciate someone to kind of jump in and maybe correct me. Essentially, as this discriminator gets more confident, I think they're saying, is it goes closer to 1 for real as it becomes better at discriminating. The loss function for the discriminator based on x is actually closer to 1, and for x hat gets closer to 0. And so what you end up having is that you saturate the gradient and you can't actually follow the gradient. Essentially, it vanishes. So you have to set it up in such a way so that it doesn't vanish, and it's a nice, smooth, continuous function, as opposed to being straight 0 to 1 when it saturates. I'm not really sure how this works, so I'd appreciate someone else's perspective on this. What they're saying is the loss is the binary cross entropy, which is the log loss of these. So wasn't clear on what dx means. I'm assuming that's the loss of the discriminator. Is that correct?
Yep.
Okay. And I guess that's part of addressing some of the pitfalls. The third one is I think something that I think Mayank has touched on a few times, which is mode collapse, which is essentially the generator learns to just map to a single point on the manifold. And what ends up happening is the discriminator says, no, that's fake. So it jumps to another point on the manifold, and it just keeps jumping back and forth. You don't discover a function to actually map back to the manifold. All you're really doing is bouncing all the way around. And I'm sure, Mayank, you have a probably better way of actually explaining this, but that is my simple understanding, is you just jumping around.
Yep. We are trying to just jump around in a manifold, as Alfredo pointed out in his excellent, practical there we can see the spiral in which the which is the manifold, and that's the correct way to explain it.
Okay. Okay, so with that, I'm going to jump into the code. I'm a product guy. I am not a developer, so feel free to jump in and correct me in my basic understanding. So the way if you go back to this document, which is the link on the page, is the recommendation in terms of training is to alternate. So you basically train the discriminator for a couple of epochs, then train the generator, and then you repeat the steps. So you alternate between training the discriminator and the generator on a continual basis. So I think that's what we're doing here. So first of all, what we're defining is the generator, which I think, as Alfredo said, is essentially you're upsampling from the Z space to get back to the X space. So NZ is the number of I guess the dimension of the Z space. This is the number of features of the generator, and essentially you're just basically doing transpose. I think that's a stride of 4. You're doing batch norm, and then you're doing a ReLU, and you're basically upsampling. Here we've got 4x4, 8x8, 16x16, 32, so until you get to like 64x64, which is the X space. So to me, that looks pretty much like a decoder, but I get the earlier points, but I'm just saying the concept is kind of similar. You're upsampling from the Z space back to the X space, and that's the generator class. Anybody want to jump in and add something, or just clarify my understanding? Nope. Okay. Hopefully that made sense. So that's the generator, which is providing the upsampling here, and then we have the discriminator, and that you can think of like as it's essentially a classifier. So it's taking like obviously the input with the number of channels, whether you have color or not, and from that it's essentially providing a classification and doing classification using a sigmoid, standard classifier based on an image, and obviously doing convolutional. One thing that he highlighted was obviously the leaky ReLU, and I think the comment on that was that if you just use ReLU, you'll have a vanishing gradient problem, because obviously ReLU has 0 for negative values of X of input. So you need a leaky ReLU to maintain a gradient so it doesn't vanish completely for negative values. So mates, anybody want to add anything to that? Makes sense, hopefully. I'm not clear exactly why it would actually vanish. I mean, I get the theory that it's if it's for negative values, but I'm thinking that wouldn't this train itself to shift the space so it's positive? But I'm not clear on that, but I'll take it at face value. Okay, anybody want to add anything to this? Okay. So one thing that was mentioned was essentially what we're using as a loss function is the log loss, which is binary cross entropy. Now, I know in the video what he said was that it's a bad idea to use this, and I wasn't clear on why. Did anybody catch that?
I think because it's a classifier loss, and they don't like classifiers. They would prefer a continuous function in their formulation.
Okay, that goes back to the original problem. I think this goes back to the unstable convergence problem. Okay, okay, that makes sense. Okay. Oh, by the way, I tried to get this up and running, and you have to kind of hack around this portion of it. You have to hard code it, or at least you need to do a sysargv. So I'm sure there's a better way of doing it. I'm not a developer, but if you're trying to recreate it, that's kind of like the key, and then I think the rest will probably be working fine. Mine took forever because I didn't have a GPU, but it seems to be doing reasonably okay. So if you're trying to redo the code, let me go back to here. Okay.
Just an interjection, really, you can use Colab. That gives you GPU. I mean, that's everybody knows.
Oh,
that
yes, yes, right.
Yeah. Okay.
Ah, yes, you're right. I hadn't thought of that. I haven't used Colab for a while.
Okay.
Thank you. Okay. So then we have the setup. So I'm not really clear on some of this stuff. So obviously the noise is random, random generation batch, based on batch size, the number of dimensions of Z. And then we classify as obviously real or fake labels 0 and 1. We define that way. So we just created labels for those. And then we run 2 optimizers, one for the optimizer and one for the discriminator, one for the generator. One thing that he did mention was that when we train the discriminator, when we're using real data, we detach this is what confused me a little bit. So I'd welcome, feedback on this. So when we're training the discriminator and we're using fake labels, we detach we do a detach so that we're ignoring the gradients. I'm wondering, why did we do that? Why do we want to ignore the gradients for fake labels? I'm not sure if anybody actually has gone into it. I'm thinking that
because it would be moving the generator in a wrong direction, right? You see here, as we discussed before, the loss functions for discriminator and generator are pulling in opposite direction. And if we would allow the gradient flow to generator, we would train generator to generate worse images. So we need to detach here.
Okay, thank you.
I thought also about this, but my question is, here we are, when we call step, we're using optimizer D, which was created using only the discriminator parameters. So I wonder if this is real necessary, or if this is just to avoid calculating the gradient, since they won't be needed anyway, just to save time, for example.
It's needed because in other case, the gradients would be probably accumulated for discriminator parameters. So
okay, got it.
Yeah, cool.
And then obviously when we go into training, we go into the 2 steps, which is the first one is we train the discriminator network. And for the discriminator, we do it in, as I said, in 2 parts. The first is we feed it real data from the data loaders, compute the loss, and then accumulate the gradients with backpropagation. and then feed the discriminator data to the generator using fixed noise. And this goes back to the point. We detach the fake data to stop gradients from propagating to the generator while we train the discriminator. Okay. And I'm assuming we only need to initialize the gradients. We zero grad once in the beginning. That's just standard stuff. But I thought best practices was not to zero the weights. Then you have the symmetry problem. You need to break symmetry. So maybe I'm overcomplicating it. Should we just put random numbers into the gradient, zero grad, instead of like zeroing it?
Zero grad is not zeroing the weights. It just resets the gradients. Each parameter has like dot grad attribute to it. And there the gradient information is stored. It's of the same shape as the weights, but that's gradients. And we want to like reset gradients after we applied those for weight update each time. But here he just says that we want to accumulate gradients corresponding to fake labels and real labels, and then do one step having both those like gradient components, we can say, right?
Okay, that makes sense. I'm a product guy. I'm not a developer, so I would welcome anybody who wants to kind of come in and kind of like go through this code. I know enough to be dangerous, but you know, I just look at this and kind of like, you know, this basically is what we discussed up here, which is we zero out the gradients as Arto mentioned. We basically label the data, and then we basically run that, generate the cost function, do backprop, and then the output of the discriminator, I believe. So I'm not a developer, guys, so feel free to jump in. So let me know if I've missed anything. So essentially, I won't go through the code. You know this probably better than me. So once we've trained the discriminator, then we go into obviously training the generator, which is zero the gradients. We're using, for the generator, obviously fake labels are real. We output that through the discriminator class that we have. We're pumping in fake data. We generate the cost function and do backprop. Anyway, I'm not a developer, so I welcome anybody to kind of like go through the code and just, you know, explain it much better than me. So feel free, anyone if you want to jump in. Okay. So with that, I just open it up for questions and see any feedback or what you guys think about what Alfredo said. Questions you may have, whatever.
I think so. The code and the steps here are well explained in the Alfredo's video.
Okay.
If somebody has any other questions than what has been already been explained, then yeah, please feel free to ask. But it's kind of like self-explanatory in many senses. So I think so. Most of the people here already get it. So
Okay. Good.
Yeah.
Good. I was worried I was boring everyone to tears. I probably am anyway. Okay. If there's no questions, then, you know, I appreciate your time.
Yeah,
and
I
wish you
have like a quick
please.
question. So that's if anyone has some experience with training Gans. I just have like a little. I just played with it, not never done it like for some really serious task. But from my perspective, it's like they are really tricky to train. And yeah, I'm just wondering if anyone is familiar with any application of GANs like in production or something like that. If anyone like interacts with interacted with GANs in any like real world scenario, just not just like really cherry picking nice images.
Yeah, we do it all the time. When you're trying to in the block Gans example, the slides that I presented, uh, that had a result of those object features that you can just remove by highlighting a particular object. Suppose there's a car or a person, and you want to remove that from a scene. You just highlight it, that person or an object or a car, whatever that is, that will be disentangled and will be removed from the scene, and those holes that are there will be filled via the image in painting kind of uh, uh, latent space extension. So yeah, there's one. Then music and games. Uh, the world model stuff in reinforcement learning. There are many applications, and specifically, if you go to the NVIDIA's website, there is a Gaugan, which artists can use to as a paintbrush to have some initial iterative thoughts about the ideas in which how you can create some initial paintings with try to with respect to try to kind of like have an intuitive first feeling, and then you can uh, yeah. And this is a good work too, the e-commerce GAN, uh, in which you are trying to uh, generate data with respect to the products and services that you have. So there are multiple applications in which it's currently being used. So yeah.
You mentioned reinforcement learning, Mayank. Where that's an interesting one. Where I don't see the nexus there. What are you thinking?
The for example, in the game GAN, that paper came out in CVPR. The learning to simulate dynamic environments with game GAN, in which I think so. I think two. So it was in the slides. So last time I've shared the slides. Take a look there. You can find.
You're talking about this game GAN.
Yep. So here, this can be simulated. This can be extended while trying to generate uh, uh, training examples for your reinforcement learning agent. In the real scenarios too, in which some sort of a simulator with respect to some cars or other stuff, some autonomous simulators. It's with respect to the noise that you're trying to inject. So that will be dynamically created. So here, that's what they are trying to do. And this is an example of it.
So my impression is that variational autoencoders, obviously not the same thing, but they can do pretty much the same thing as Gans or similar things. They're more stable, easier to train. So when would you use one over the other?
That depends upon a particular use case in which what you're trying to do. Suppose Gans were better up until 2019 or 2020, but now VAEs, the variational autoencoders have taken a step ahead due to the stableness of the training and the exact nature of how you are trying to get the samples from the latent space. So, for example, if I try to give you a real product example, VAEs are better if you're trying approaches with respect to the facial manipulation, for example. Currently, they are the state of the art. If you're trying to change the lighting and the facial features, those latent space manipulations, they are with respect to because if I go into the details, how do they do it? There was a recent paper called Style Flow, in which Adobe has used an example of the style Gans too, and they have used inverse ODEs. That's the one of the ways that you can. That's the third way. There's a GAN, there's a VAE, then there's a ODE too. So yeah, the combination of approaches are required in many cases, but to get back to your initial query, where VAEs are better, where GANs are better, it depends totally upon the context and the subset of the problems that you're trying to solve. So there's no one answer to fit all, but yeah.
Okay.
Yeah.
Thank
Great,
you.
thank you. Thank you. It was very informative.
Yeah, thank you. Cool. Any other questions? If not, we'll let you go. Have a wonderful weekend of what's left of it. Speak next week.
All right.
Thank
Thank you.
Thank you, guys.
Yes, thank you. Bye.
Cheers. Thanks.
Thank
Bye.
you. Bye.